Okay, so I say I do data science, right? But data science covers a broad church, so what do I actually mean when I say data science? When we are here this afternoon, we're going to hear a lot of talks, and you will start to understand the breadth of data science and AI and that kind of thing. But what do I do? What do I mean when I talk about data science? So this is what I do. I build internet-scale data analytics platforms, and I build the teams to operate them, and then I predict the future, okay? Whatever predicting the future happens to mean for your organization, all right? And we'll get into some of that later on. And Gen AI, because everybody does Gen AI. It's a bit like blockchain. Everybody remember blockchain when that was a thing? Yeah, it's a bit like that, right? Mostly you don't need Gen AI until you do need Gen AI, and then Gen AI is the absolute solution to that problem. Okay, I want to make a quick disclaimer. First of all, just before we carry on, I'm going to tell you how we solved the problem for national highways in the UK. I don't want that. I don't want that to make you think that you must be an idiot to hire Gary Short because he comes and he solves your problem, and then the next thing he does is he gets up on the stage and he tells all your competitors how it was done. Right? That isn't the case. National Highways in the UK is a kind of arm's length government department. So basically, the taxpayer owns the technology, technically, I guess. Anyway, but more importantly, they already wrote an academic paper about the solution that we came up with. So it's in the public domain anyway. I like story archetypes. I like story archetypes when I am presenting because it kind of keeps the story flowing. So the story archetype that I've chosen for this afternoon is the voyage and return. So everybody's familiar with the voyage and return story archetype, although you might not realize that you are. It's in lots of movies. It's in Dune. People have seen Dune. People have seen Everything Everywhere All at Once, and even Barbie. So that kind of covers a broad church there. All right, all of these are the voyage and return story types, right? And so we're just going to follow along that story archetype as I explain what it was we did. Okay, so first of all, the departure. Okay, our hero departs and leaves his familiar world, right? So what was my familiar world? This is my familiar world, I told you before. Okay, I build internet-scale data analytics platforms and the teams to operate them, and then I predict the future. That's what I was doing. And I was doing it for National Highways. As I said, they're a kind of at-length government organization in the UK that look after the roads. This is not every single road. Some roads are maintained by the local council, but the strategic road network is basically your major A roads and the major M roads in the UK. Technically, just England, right? Because Scotland has its own national highways called Transport Scotland, but of course, England, theirs is called National Highways, but they only look after their own. So this is what we were doing. As I say, I was well within my my world was well within its normal frame. What I'd done was I had created an internet-scale analytics platform for National Highways to use and to do data science on, and we were all out celebrating the launch of that actual product. You can tell we were celebrating the launch here. You can tell this was Gen AI, right? This poor woman has her arm grown out of her left ear. Not entirely sure why. You can tell this was generative AI, not only because, of course, they've got an arm coming out of their left ear, but of course, when I say I want an image of a group of nerds celebrating the launch of a successful product, it says certainly you can have some nerds, right? They have to be ethnically diverse. They'll be ethnically diverse and gender diverse, but they will all be nerds, and I will signal this by making them all wear the same glasses. Right, that's how you know they're nerds, as opposed to just four random people in a beer garden. So there we were. We were celebrating the launch of this. Product. And one of the guys who had been seconded onto our team from the actual business said, "Well, now that we've got this thing, Gary, it's great and all that, but how am I supposed to use it? How do I find the initiatives that I'm supposed to run on this platform?" And I said, well, there are lots of ways to do it. I said, but the way I do it is I would go around the leadership of the departments, and I would say to them, what is your biggest problem that you would like solved within the next 3 to 6 months. Because when you've spent a year to 18 months launching a large cloud-based analytic platform, you don't then want it to be another 18 months before you can solve your first problem, because then people are starting to look at, well, this is 3 years worth of investment. I haven't seen anything yet. So once you've got your platform into the internet and on the cloud and ready to go, you want to solve your first major problem as quickly as you can in that 3 to 6 months. So I said, so what I would do is I would go around the departments, I would speak to the department leaders, department heads, and I would say to them, what is the biggest problem that you think AI could solve and it take about 3 to 6 months? And then you just treat that like a sales funnel. They'll all tell you theirs, it all comes in at the top and into a big kind of hopper, and then you filter it as you go out. Well, we can't do this one because we don't have the budget. We can't do this one because for this reason, and then you'll have some that left at the bottom, and then just make your choice on the ones that you think will bring the biggest bang to the buck for your customer. And then at that point, the guy said to me, that's all well and good, but my problem is impossible. And that brings us on to part 2 in the voyage and return story archetype. It's the ordeal. Our hero faces danger or becomes lost and confused. That happens to me quite a lot. I become lost and confused quite regularly. Oh, we're all over the place. It's just going to randomly jump to slides. That'll make the talk even more interesting. Okay, this is the actual next slide. So what he said was, I said to him, why is your problem that you want to solve, why do you think is impossible to solve? And he said, because what I need to do is I need to build a model to predict asset risk on the strategic road network. And I went, okay, sounds complex, but fairly straightforward so far. And he said, I have no data. And I said, well, how can you have no data? It's like I see people out working on the roads all the time, right? I can't drive from here to there in the UK without lane closures and stuff like that. So I feel certain that you have data about that stuff. And he said, no, we don't, because we outsource that to somebody else, and they have the data, and we don't. We could get the data, we could ask them for it, but that would be a change to the contract for which we would have to pay a hefty fee, and we don't want to do that. So we have no data. And I was like, okay. So let's just examine why that's important for a start. So let's just have a quick aside about what a model is. Now, if you ask, the great thing about data scientists is if you have 3 data scientists in a room and you ask them to define a model, you'll probably get 4 definitions of what a model is, okay? So here's how I define it. I like to think of a model as being like a timeline, okay? Over here is the past, this is the present, and over here is the future, okay? Now, you can do data science all along this timeline, okay? If we're doing it in the past here, some business may have questions like, how many widgets did I sell in the 3rd quarter of last year? Compare that to 10 years ago. How is my company growing? Okay? Well, that's fine, because we can use all kinds of statistical analysis on that data that's in that database, right? But if we turn around and we look this way into the future down the timeline, and we want to ask the same question, how many widgets will I sell in the next quarter? We can use, or we want to use, the same statistical techniques, okay? But we have no data. So instead, what we do is we construct a model of what we believe the world in the future is going to look like, and then we use those exact same statistical techniques on that model as if it was data. So a model is just data in the future, right? Data in the past, model in the future. That's all a model is. And what this guy wanted me to do was to create a model that would tell him what the risk was on the strategic road network, the risk of asset failure, in the future, not in the past. So we need a model, not data. Okay? Now, normally what you do is you would look to the past, and you would look to the data in the past, and you would use that to build your model in the future. But he doesn't have any data. So that makes it extremely difficult, in his view, impossible, to make a model that predicts the future. So let's get a feel for the size of that problem. This is how the assets on the strategic road network are built up, right? At the very bottom, at the very lowest granularity, you have an asset, right? And an asset is just anything on the strategic road network that is required to make the strategic road network function, but which isn't actual road, right? So it's everything else. It's the barriers, it's the lights, it's the signage, it's the tunnels, it's the telephones, all of those kind of things, okay? And they get grouped together in what's called a link. And the link is the smallest granularity piece of road, such that it runs from junction to junction, right? So if you are on the motorway and you get on at one junction, you cannot leave that motorway until you get to the next junction, okay? That piece of road is called a link between two junctions. Basically, if you enter at one end, you must leave at the other end, right? That's a link. And that's the end of the things which are physical things. Everything above that are just imaginary abstractions of that. A section is just a group of links for administrative purposes. An area is just a group of sections for administrative purposes. And then regions are groups of areas. And then right at the top, you have the entire strategic road network. So what this gentleman wanted to do was to calculate the risk at the asset level. And there are 6.3 million assets on the strategic road network in England. And Wales, I think it covers Wales as well. 6.3 million assets spread up over right from an individual drain on an individual road right up to the entire strategic road network. And he wants to know what the individual risk is at the asset level and then aggregate it all the way to the top. That's the size of the problem with no data. Part 3 in our story, if you follow along a story or a movie like Dune that follows this voyage and return archetype, is the realization. Our hero gains an insight or learns a lesson. So what insight did I get? Or what insight did I have already? And the thing was, I never thought this problem was impossible, even when he described it. I didn't think it was impossible for 2 reasons, right? Firstly is this reason. In my youth, many, many decades ago, when I was a teenager, I was a member of the Army Cadet Force in Scotland. And we did lots of things, and because it was, in fact, it was almost in black and white back in those days. It wasn't before GPS, but it was before everybody had GPS, right? You basically had to be a company if you wanted GPS. So when you wanted to know how to get from here to there, right, you actually had to read a map. And there was a part of that was being able to judge the distance between 2 points, all right? And there's lots of ways to do it, and how we used to do it was with a paper map and a plastic ruler, and you measured the scale on the bottom of the map, and you marked it, made scratches on your ruler, and then when somebody said, how far is it to that junction or that farmhouse or that church or whatever, you just laid it on the map, and you went, well, it's roughly 3 miles, okay? But one of the things they asked us to do was, well, what happens if you lose that ruler? What happens if you lose that map, right? How are you going to be able to judge the distance from here to there, okay, if you don't have any tools to do it with, right? If you have to make a guess, an estimate, how do you do that? And they taught us lots of techniques. And one of the techniques that we learned was called group average, where basically everybody made their own guess independently, right? And then as a section commander, you went round and you wrote down those guesses, and then you basically took an average, right? And what I learned doing that back then was we all knew how to calculate the distances, and we'd been practicing that. And so we knew what 2 and 3 and 5 and 600 meters looked like because we've been practicing it for ages. And what I learned was, if you're a subject matter expert in something, and you get a group of subject matter experts in something, and you ask them to make an estimate about something, you're pretty much bang on, right? You're pretty close to the actual measurement. What I found when I was doing this technique in the cadets was that there was very little difference between what a group of cadets judged the distance to be and what the actual measured distance to be. So when he said, we have no data, I thought to myself, we can still do this, because never in the history of ever has the strategic road network in the UK been closed because a bit of it fell off, right? I'm sorry, it's broken. You can't use the motorway today. Why not? It's just broken, right? That's never happened, okay? And that's never happened because the people who are charged with maintaining it know what they're doing. Okay, so you might not have the data in as much as you don't have it in a database somewhere where you can go and look it up. But individuals within your organization, they know the answers to the questions that you have, right? Because they do it day in and day out. And so that's the first reason that I knew that this problem wasn't as impossible to solve as he thought it was. And the other reason that I was pretty confident that I could solve this problem was that by this time in the afternoon, I was 3 pints in, and 3 pints Gary can do pretty much anything. So we're going to build a model to predict asset risk on the strategic road network, right? That's a big ask, right? So if I say to you, if I said to any subject matter expert in maintaining parts of the strategic road network, what is the risk on the entire network? They would have no idea, right? No idea, because that's not what they do, right? So what we have to do is we have to constrain the actual question that we're going to ask them into something that they could possibly know about, and then we'll aggregate from there. So the question that we went to was something like this, right? So you form the question like this, and this is just an example to show you how to go from something which is huge, right? How do you carve an elephant, right? How do you eat an elephant? Slice at a time. Something that's huge, down to something that's actually manageable. And here what we did was, as an example, we say, given 20% less maintenance, what is the probability that this given drain of this given type fails in the coming fiscal year? Okay? So if you have any given drain of this type on the strategic road network and you do no maintenance, what do you think the probability is, as an expert, that that drain would fail? That's a much more manageable question. Okay? That is what they do, that's what they understand, and that's what we ask them to do. So what we do is, first of all, I'm a bear of little brain, and so I always do the simplest thing that works, right up until it doesn't work, and then we do something else, okay? So the simplest thing that works is we work out, under the category, what are all the ways that a drain could fail, okay? And these are a list of some of the ways that drains can fail. The one that got me, that I liked, was illegal connections and misuse. It's like, what, literally people will just build things and connect it to the drain system of the strategic road network. Oh, yes. Apparently so. It's like, I don't, but do they think no one was going to notice? I mean, it's like you build a restaurant or something and you connect your drain to, yes, apparently so. That one baffled me. But and they go from the obvious ones to blockages right down to things like ground conditions, right? So if the ground, if you have subsidence or something like that, and the ground gives way under your drain, then the drain can fail. Okay, that one's not very likely. So this is the simplest thing that could work. So what we've got here is a list of all the ways that the assets could fail, and the subject matter expert's opinion of what the probability is that that failure condition will happen. Part 3 of our story. So if we are following the voyage and return archetype, then part 3 is the realization. Our hero gains an insight or learns a lesson. Okay? So what did I learn? What I learned was most subject matter experts aren't. Right? Most subject matter experts aren't actual subject matter experts. And that baffled me for a while. I said, I do not understand this. Right? You clearly have no idea what you're doing. You, on the other hand, absolutely do understand the minutiae of what it is of your part of the area that you are maintaining. I don't understand how you two are as successful as each other, right? And I was noodling this problem on one walk when I was walking the probability pup. And I suddenly remembered a story that my grandfather told me, and that actually was the solution to this problem. And a story he told me was, now my grandfather during the war was in the Navy, right? He joined the Navy because what he knew of war was, as he told me, what he knew of war before the Second World War was all the stories about the First World War, about trench warfare and all the rest of it. And he said, so I joined the Navy. No trenches in the Navy, son, right? Very difficult to dig a trench in the ocean. Smart man, my grandfather. But he told me the story about when he was at basic training, right? And he had done some misdemeanor or other, right? He was never very clear on what the misdemeanor was, okay? But there was some kind of misdemeanor, some kind of infraction, and that's punishment. He was told to get out and whitewash around the white lines on the parade square. And he was like, fine, this is not a great way to spend the evening, and he's doing it, yada, 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 complaining, muttering away under his breath, and he knocked over the tub of whitewash, and it went splashed everywhere. Now, there is nothing that you can do about that, right? There's no solution to that problem. You cannot get that whitewash back in that tub. So what he did was, he painted it very neatly and very accurately into a square on the line, and then carried on. Nobody noticed, right? And he went about his business at basic training. No one ever said anything about the lines or the square. After the war, about maybe 10 years, he says, after the war, the word's just going straight out of my head. That's terrible. When lots of old people get back together again. Reunion, thank you. There we go. That's the word. Excellent. Well done. Just, you see, I'm more sleepy after lunch than you guys are. So there was a reunion of people who had been trained at that particular training establishment about 10, 15 years after the war. He went back there. He went back there, and lo and behold, this whitewashed square was still there. Because the next guy came along and went, I have no idea what that square is for, but look at it. It's perfectly, and it's supposed to be there, clearly, because, it's there. And they just painted it, right? 15 years later, that square was still there. And I realized that's what these people were doing, right? Some people really understood what the problem was and really understood how to solve the problem, and other people were just doing what the guy before them did without really understanding it. And so when we're using this technique, it's important to separate these two people out, these two types of people out, so that you're dealing with the true subject matter experts. Did that go? Okay, this is going to be an interesting talk. I press the button, it gives me a random slide from your talk. Okay, so what we have to do is we have to make it easier to be able to estimate that probability, right? If I say to you, what do you think the chances are that it's going to rain tomorrow, right? And I ask you to give me an actual number. That's quite a hard thing to do, okay? So we don't do that. What we do is we do this kind of thing. We ask them to estimate a range, and we do it this way. I say to them, I want you to give me a value below which you think it is not possible that this measurement could possibly be. Now, we don't have anything for measuring that. We don't have a tool that we can go and measure the risk on the strategic road network with. But imagine we did, right? Imagine tomorrow I invented a tool that you could just walk up to an asset, shine it on the asset, and it tells you the exact probability, right? That value that I ask you for, right, should be at a level whereby if I said I've invented this tool and the tool says it's a number and that number is less than what you think, your first thought is your tool's broken, right? Not, oh, I've made a mistake with my estimate. You should be so confident, right, that your first thought is that tool is broken. And once you've done that, I want you to call that number the minimum. And then I want you to do the exact same thing, but with a number above which you think it couldn't possibly be, okay? Again, to the extent that if I invented a tool and I told you the number was more, you would say your tool's broken. And I want you to call that number the maximum. And then what I want you to do is I want you to pick a number not in the middle of that range, but a number that splits the two halves of that number range so that you believe there's an equal probability that the true value will be in either half. Okay? Try to avoid selecting the middle because it's almost never exactly in the middle. But imagine you have a slider and you're sliding between that range and you want to move it so you think, yeah, I think there's a 50-50 chance now that the true value is in one of those pockets, right? And then whatever that number is, we're going to call that the median. And then I want you to do the exact same thing twice more, okay? But instead of using the full range, I want you to use from the minimum to the median that you just got as if that was the maximum and do it again, okay, within that bottom half and call that Q1. And again, take the median, but this time as the lower value and the maximum as the upper value and select again in that top half and call that point Q3. So we ask them to do this, and they come out with this range, and that's actually much easier. It's much easier to ask somebody to describe a distribution that they are confident absolutely does contain the right answer, but not actually state the answer itself. Just describe the distribution that holds that answer. So that's what we did next. The trouble with that is, the next thing that we realized was that doing it that way assumes that everything is the same importance, okay? And it's not, right? Some maintenance is far more important than others, right? And the way to understand which maintenance is more important than others, because everybody has their own opinion about it, and when you first start to discuss this, right, people say, oh, well, it's important you do this kind of maintenance, it's important you do that kind of maintenance, and blah, 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 blah. The way that I found best to cut to the chase was, if I said to you, you've got 20% less budget than you did last year, what maintenance would you not do? And you go, well, I wouldn't do this one. Fine, that one's on the bottom. And then I just keep going until they've run out of maintenance tasks, and then the very last one they had is the most important one. And now we've just ranked them. And it's actually easier to ask somebody, I found, for this particular task, it's easier to ask somebody what they wouldn't do if their budget was cut versus what maintenance is important and what maintenance is not, right? It just gives them another way to think about it. And then what we did then was we added a weight column to that. So we weight each of these probabilities in the calculation. And then the last thing that we wanted to do was we wanted to assess the client's appetite for risk, okay? Because risk is not all the same. What we want to do is we want to emphasize risk probabilities above their comfort level, and we want to kind of minimize it doesn't really matter. We want to minimize the risk below their threshold, below a threshold that they don't care, right? So basically, if it's more than they care about, we want to emphasize it, and if it's less than they care about, we want to minimize it. And the way we do that is with a sigmoid function. So this is the formula for sigmoid function. We don't really need to get into it, but basically, it works like this, where f of x is your aversion to risk, right? A measurement of your aversion to risk. E is the base of the natural logarithm, which is just one of these mathematical constants. X is the probability of failure, right? So at this probability of failure, how much would you care if it failed or not? And then K is how quickly the client becomes averse, right? So if I say to you, what's the probability that it's going to rain tomorrow? And you say, I think it's 60%. And I say, okay, do you care if it rains tomorrow? And you say, well, yes, because I've got a family picnic. Okay, if I say to you, well, I think the probability is 70%, you care about that, right? Because you don't want it to rain. But if I say to you, it's 30, the difference to you between 40 and 30% chance of rain, you don't really care about that because it's less. So the difference between 30 and 40 is less important to you than the difference between 60 and 70, right? That's more important. So we use this formula to do that. And x, by the way, is the midpoint. The midpoint is, x0 is the midpoint. It's the point after which you start to care and the point below which you don't care, okay? So we interviewed a client and they tell us, I'm happy with the probability of failure of 50%, but I would become rapidly adverse to risk or losses above that value, okay? Basically, if you have to shut your section of the motorway because maintenance needs to get done, people ask you questions, right? Government ministers want to know why, right? And so you very quickly become adverse to risk above 50%. So we plug that into our formula, and we get a sigmoid model for loss aversion that looks like that. And as you can see, the dotted vertical red line is the midpoint. Everything above that midpoint, we become rapidly averse to, and everything below it, we become rapidly, we don't care about it. So let's recap. What we got from the SMEs after all of this interviewing and things like that is, on the one hand, we have a five-point weighted distribution of the probability of failure of particular assets. And we also have a way of quantifying how much they care about it. How much you care about it is qualitative data, right? But what we've done is we've encoded that. We've got a quantitative value for how much you care. So we have a distribution for the probability of failure, and we have a way of quantifying how much you care about it. It will surprise you not in the least to know that I can't do a demo because I don't have my laptop here, right? These are my favorite kind of demos. Imagine you are now looking at awesome code that never fails, never crashes, and gives the right answer every single time, and comes up with an answer at the bottom. Ta-da! Wasn't that wonderful? The issues that gave us, of course, is that it doesn't really look like how we just described. Once we'd run that calculation, we realized it was completely wrong. Okay? And the thing was, anybody here know a bit about probability? Yeah, a few people, okay? Professor at the front going, yeah, I do. I know quite a bit about probability as it happens. Yeah. Glad to see the professor's hand is up. Those of you who understand a bit about probability would realize that what we looked at with just a list of the ways of things can fail was we treated all these things as if they were independent, right? As if each of them have not necessarily an equal chance of happening, but that they don't depend on each other in order to happen, nor do they affect anything else if they do happen, right? And actually, once we ran the calculation for the first time, we realized that was nonsense, right? Actually, they aren't independent, and they do affect each other. So over here, we've got weather exposure up here, right? And we have the drain condition at the starting point, right? Now, obviously, they have an impact on the maintenance history, all right? Because if you have an old drain that's exposed to the weather a lot, it's going to need more maintenance than a new drain that's not exposed to the weather. Okay? So in fact, we realized very quickly that these things were not, in fact, independent. And what we had to do was we had to create a Bayesian network, right? For those of you who, we don't have time to explain what a Bayesian network is, it doesn't really matter. Basically, it's just a way to account for the effects that things have on each other, right? In a world where things are not independent, it's a way for us to account for how they affect each other. That's all it is. And so we realized we had to create this network. And this is just how we, so this is the exact same network, right? But this is just how we, in probability, we read this. What we say here is, this line here denotes the probability of maintenance given the weather, right? So, given the weather is bad for some value of bad, the probability of maintenance goes up, right? If the weather is good for some value of good, probability of maintenance goes down, okay? And so what we do is we put those in. Look, so the weather is mild or harsh, the maintenance is regular, it is there's no maintenance, or the maintenance is infrequent, right? So we basically codify what we mean by the dependent nature of these things on each other. Again, a brilliantly coded demo here, which shows you are running all of this code and solving all these problems and coming out with a number that, if I'd ran the first demo, you would see was different from the first demo, but actually more realistic, right? And that clued us into the fact that actually we had solved that problem, and the way we were looking at things now was far more realistic, okay? But it still had issues. So what we had, if you look at this previous, what we had in here was we were no, not that one. See, I shouldn't have gone backwards and forward. There we go. What we had here was we were back to actually putting in individual. We were back to making the same mistake. This one was really annoying because when we looked at it, we went, hang on a second, we're back to doing a mistake we already did the first time around, and we already said that was a bad idea, and we already solved that problem, and we've done the same mistake twice, right? We were putting in actual individual probabilities, and we understood that was difficult for them to estimate those individual probabilities. And so what we did was we went back to this idea here of putting in, instead of these individual probabilities, we were back to putting in our distributions, okay? This is just a mathematical notation for it's the same thing as the 5-point descriptions that we put on the slide previously. All we're doing is using a different kind of notation so it fits on the slide. And so we changed the individual probability point estimates that we were asking them to make, and we changed it back to being a distribution they were describing. And then we did this fantastic demo here with distributions. It's a bit like a Monte Carlo simulation. Who knows what a Monte Carlo simulation is? Excellent. Most people. Easiest way for those of you who didn't have your hand up, I don't know if you're just too lazy after lunch or if you didn't actually know, but I'm just going to assume that you didn't know, and I'll explain it. Easiest way to explain a Monte Carlo simulation is if I toss a coin in the air and it comes down heads, it comes down heads, right? If I do it 10,000 times and I write them all down, okay, and then I say, what's the probability of heads, what's the probability of tails? What is the probability of heads? 50%. Excellent. That's a Monte Carlo simulation, right? Monte Carlo simulation is just basically doing the same thing, running the same experiment over and over, and then calculating some form of average for the results, okay? And that's what we do here. Remember I said in the network we had a distribution instead of a point value. What we do in the Monte Carlo simulation is we just randomly sample from all of those distributions to get a point probability for the network, and then run the calculation over the network. And then we do that 10,000 times, and then we have the probability at the bottom, right? And that gives us, it turns out, a very accurate probability of the failure of the asset. So our hero, the last part of Voyage and Returns, our hero returns with a new perspective. And this new perspective in actually working out this entire methodology end to end and then developing it with a company and putting it into practice has given me a really good methodology for solving problems like this. And it basically solves problems in the class of, I want to build a model to solve my AI and data science problems, but I have no data. Therefore, there's nothing I can do. Well, actually, there is something that you can do, right? You can adopt this approach and this methodology, and that will get you there. Okay, that is pretty much it. I think we've got about 2 minutes to go. You can have a quick look at my lovely probability pup. If there are any questions for the audience, if there are any questions, I will quickly take one or two just until the end of time. If not, feel free to reach out to me on social media, LinkedIn, whatever, ask me your question, and I'll get back to you. Okay, thank you very much.
Thank you very much, Gary. That's really great.
No problem.
Do we have any questions for Gary?
Nope. Excellent. That means...
Anyone at all before we go?
Not a problem. It means I can get to go and grab some ice cream and an adult-friendly beverage. As I said before, if you do think of a question later on, that's totally fine. Just reach out to me on social media, and I'll get back to you. All right. Thanks very much.
I was going to ask Gary, sorry.
Oh, yeah, if you want to ask
I was going to ask one question, maybe.
Sure.
So you created this Bayesian network. Did you use some pre-existing software? What kind of tools would you recommend for this kind of thing?
So that's a great question, actually. Great question. There's a lot of tooling around Bayesian networks, and what we found is that they don't scale to where we needed them to scale. So what we did was we basically wrote our own tooling. So what we did was we had. Is anybody familiar with the dot notation? Does anybody know what that is when I say it? It's a dot file, which is how
the graph.
The graph viz,
yeah.
Right? So if you ever use the tool graph viz, that has a file notation called dot, which is how it gets called dot notation. So what we did was we literally got people in to draw. We would draw. The data scientists, we would draw what the Bayesian network was. We'd draw all of the independent things. Then we say to the subject matter experts, how are these things connected? And they'd say what they were connected. And then along each of the lines, we would do those distributions that I was talking about. And then when we'd done that, what we'd do is we would create a dot file of that network. And then we just wrote, I wrote a piece of software that consumed these dot files. Each of them had a unique identifier. You then looked up the unique identifier in just a standard SQL Server database to find out what the distribution was, then took the graph, the Bayesian network, and the data from the database, put it together to form that part of the whole network, and then sent that as a job to basically to your favorite MapReduce framework, right? Whatever it happens to be, right? So basically, cloud-based compute, right? And then we got the answer back, and then we aggregated all those answers. So really, we ended up having to write our own because the tooling that we found doesn't scale to that kind of level. It doesn't scale to 6.5 million assets with all the various ways they can fail. It just doesn't scale.
Fantastic. Thank you very much, Gary.
Okay, thanks very much.